Hey everyone, welcome back to Chem Story. Today, we're diving into one of the important substitution mechanisms in organic chemistry, the SN1 reaction. We'll talk about how it works, what affects the reaction rate, and what happens to the stereochemistry along the way. Alright, let's get started. Let's break down the SN1 reaction using tert-butyl chloride. Unlike SN2, which happens in one concerted step, SN1 takes two. First, the bond between the carbon and the leaving group breaks. This forms a carbocation, and that's the slow step. It takes energy to break the bond, so it's endothermic and has a high activation energy. That's why this step is rate determining. Once the carbocation forms, the nucleophile jumps in. Since the carbocation is flat, trigonal planar, the nucleophile can attack from either side. That gives us a mix of products, often a racemic mixture. So what really matters in SN1? Two things: how easily the leaving group leaves, and how stable the carbocation is once it forms. That's why substrate structure and solvent choice are so important. And that's the big picture behind how the SN1 mechanism works. Now let's go over the key characteristics of an SN1 reaction. First, it's called unimolecular nucleophilic substitution. That just means the rate-determining step involves only one molecule, the substrate, which also acts as the electrophile. So the rate law looks like this. Rate equals K times the concentration of tert-butyl chloride. Only the substrate matters. That makes it a first-order reaction overall. Second, it's a two-step process. Carbocation formation comes first, and that's the slow step. Then the nucleophile attacks. And third, SN1 reactions are usually exothermic. Energy is released as the new bond forms between the nucleophile and the carbocation. So to sum it up, SN1 is a two-step first-order reaction that depends on how well the leaving group leaves and how stable the carbocation is in between. Alright, let's take a look at the energy profile for an SN1 reaction. On the x-axis, we've got reaction progress. On the y-axis, energy levels. Since SN1 happens in two steps, you'll see two peaks on the graph. Each peak represents a transition state. The first peak, TS1, is the big one. It's where the leaving group breaks off and the carbocation forms. This step needs the most energy. It's slow, and it's the rate-determining step. After that, the nucleophile jumps in. That's the second step. Smaller energy barrier, faster move. We pass through TS2 and head down to the final products. Overall, SN1 reactions are usually exothermic. The products sit at a lower energy level than the reactants. Now let's talk about nucleophiles in SN1 reactions. In SN2, the nucleophile drives the reaction. But in SN1, it waits. The nucleophile doesn't show up until after the carbocation forms, so it doesn't need to be strong. In fact, weak nucleophiles work just fine, especially if they're small and not too bulky. Most SN1 reactions take place in polar product solvents, and in many cases, the solvent itself acts as the nucleophile. When that happens, we call the reaction solvolysis. If the solvent is water, we call it hydrolysis. If it's an alcohol, we call it alcoholysis. Either way, the nucleophile just steps in once the carbocation is ready, making weak nucleophiles totally acceptable for SN1. Next, let's talk about how the structure of the substrate affects the SN1 reaction rate. The trend is clear. The more substituted the carbon, the faster the reaction. Methyl halides barely react. Primary alkyl halides? Still slow. Secondary ones? Better. But tertiary alkyl halides? They react the fastest by far. That's because more substitution means more carbocation stability, and in SN1, that's everything. To see this in action, let's look at some actual data. Comparing SN1 reactions of alkyl bromides and water, methyl bromide barely reacts. Primary bromide is slow. Secondary picks up the pace. And tertiary, it reacts over 1,000,000 times faster than the primary. That huge difference comes down to one thing: how easy it is to form the carbocation. So what's behind this reactivity trend? It's all about carbocation stability. In SN1, the reaction can't move forward until the carbocation forms. and more stable carbocation ions form more easily. Tertiary carbocation ions are stabilized by electron-donating alkyl groups, making them much easier to form. But primary and methyl carbocation ions, they're unstable, and the reaction basically doesn't happen. So when it comes to SN1, the more stable the carbocation, the faster the reaction. Now let's look at how electron density maps help us visualize carbocation stability. Start with a methyl cation, CH3+. You'll see a large blue region. That blue zone shows low electron density, which means high instability. But as we go from methyl to primary, secondary, and then tertiary carbocation ions, that blue region gets smaller. Why? Because each alkyl group donates a little electron density, helping stabilize the positive charge. By the time we reach a tertiary carbocation ion, like open parenthesis CH3, close parenthesis 3, C+, that positive charge is spread out much more evenly. Let's bring that to life with an energy diagram. We're comparing two SN1 reactions, one forming a secondary carbocation ion and the other forming a tertiary one. On the y-axis, we've got energy. On the x-axis, reaction progress. Now look at the curves. The secondary carbocation ion has a higher activation energy. We call that EA1. The tertiary one, much lower. That's EA2. Why the difference? It all comes down to Hammond's postulate. The rate-determining step in SN1 is carbocation ion formation, and it's an endothermic step. Hammond's postulate tells us that the transition state resembles the intermediate, in this case, the carbocation ion. So if the carbocation ion is more stable, like in the tertiary case, the transition state is also lower in energy. That's why the barrier, EA2, is smaller. In contrast, a less stable carbocation ion raises the transition state energy, and that's why EA1 is higher. Bottom line, stable carbocation ions lower the activation energy and speed up the SN1 reaction. But not all substrates are cut out for SN1. Let's look at some that just don't work. First up, vinyl and aryl halides. They'd have to form sp hybridized carbocation ions, and those are incredibly unstable. The positive charge can't be stabilized well, so the reaction doesn't happen. Then there are bridgehead halides, where the leaving group is stuck on a rigid bicyclic structure. To form a carbocation ion, the carbon needs to become planar, but in a bridgehead position, that geometry isn't possible. So again, no SN1. In SN1 reactions, the leaving group plays a key role. It's the part that leaves first, forming the carbocation ion. And since that's the rate-determining step, a poor leaving group can slow everything down. So what makes a good leaving group? It needs to be stable on its own, and weakly basic. In most cases, that means it's a conjugate base of a strong acid. Great examples: iodide, bromide, chloride, hydrogen sulfate, tosylate, and water. All of these are reliable leaving groups for SN1. A few moderate ones, like acetate and ammonia, can still work, but not as efficiently. Now let's talk solvents. Solvent choice can make or break an SN1 reaction. Why? Because SN1 forms a carbocation ion, and that carbocation ion needs to be stabilized. Polar product solvents, like water or alcohols, are perfect for this. They can form hydrogen bonds, which help stabilize both the carbocation ion and the leaving group. The more polar the solvent is, the better it supports the reaction, and we can measure that using the dielectric constant. Higher dielectric constant, faster SN1 reaction. Now let's see what the actual data tells us. A tertiary alkyl halide reacts slowly in pure ethanol, but once you start adding water, a more polar solvent, the rate shoots up. With 40% water and 60% ethanol, the reaction is 100 times faster than in ethanol alone. At 80% water, it's 14,000 times faster. And in pure water, the rate is 100,000 times faster than in ethanol. So why does this happen? Polar pronic solvents help stabilize the key species in the reaction. First, they stabilize the positively charged carbocation ion through dipole interactions. Then, they also stabilize the leaving group, usually a halide ion, by forming hydrogen bonds. This dual stabilization lowers the activation energy, making it easier for the reaction to move forward. Now compare that with polar aprotic solvents. They can stabilize the carbocation ion, but they don't do much for the leaving group. That makes them less effective in SN1 reactions. Now let's talk about stereochemistry in SN1 reactions. One of the key features is racemization. You end up with a mix of both enantiomers. Why? Because the carbocation intermediate is planar. Once the leaving group leaves, the carbon becomes trigonal planar, flat like a tabletop. So the nucleophile can attack from either side. If it comes in from the same side, you keep the configuration. If it comes from the opposite side, the configuration inverts. And since both are possible, you get a racemic mixture, equal parts of both enantiomers. But that's not all. Sometimes, the carbocation can rearrange to become more stable, shifting a hydrogen or alkyl group before the nucleophile even attacks. That means you can end up with a product from a totally different position. We'll explore those carbocation rearrangements in the next lesson. That wraps up our discussion on SN1 reactions. We looked at how the mechanism works, what affects the reaction rate, and how stereochemistry plays out. The big ideas? SN1 favors stable carbocations, works best in polar product solvents, and often gives racemic products because of the planar intermediate. Next time, we'll dive deeper into carbocation rearrangements and see how they shape the final product. Until then, review the key concepts, and I'll see you in the next one.